Hey Physics 2211! In this lab, we're going to discuss Newton's second law, or the momentum principle, in order to analyze the motion of a falling object. To review, Newton's second law is also called the momentum principle. This means that the change in an object's momentum is equal to the force times the change in time over m, remembering that momentum is the tendency for an object to resist change in motion. In this lab, we're going to observe a falling object experimentally, analyze the forces acting on the object, and obtain experimental data using Tracker, and then use Newton's second law to model the motion in Glowscript. We'll use one assumption of a constant non-zero force, the force of gravity, and also a non-constant force using the force opposing the motion. Creating these two computational models, we're going to compare both of them and ask ourselves these questions. What do the differences mean? Exploring the idea of terminal velocity. And what if we threw an object downwards? What changes might occur? We're going to have to review some physics principles, including Newton's second law and net force. Net force are the sum of all of the forces acting upon an object. When Newton's second law has an Fnet of 0, it also means that the change in momentum will be 0, as we showed in the last lab. However, when Fnet is not 0, that means that there will be a positive change in momentum. In the video, we used Tracker to track the position of the object, therefore the speed and acceleration. These are the graphs of position and velocity showing the following trend lines. Notice how this is consistent with the momentum principle, which can be simplified to the change in position is equal to 1/2 the acceleration times time squared plus the initial velocity times time. This is a very similar polynomial. Using this data, we could create a Glowscript model, assuming that the force diagram on the yarn is only the force of gravity acting in the negative y direction. The starting position, velocity, mass, start and time increment were pulled from Tracker. Using an Fnet of negative mass times acceleration due to gravity, I updated the position of the ball at each time interval using the momentum principle. Using the position output of Tracker, I was able to create this graph. You can see that the shapes of the Tracker and Glowscript models are very similar. However, the Glowscript model changes position slightly faster and has a steeper slope than the Tracker model. Our first model didn't take an important force into account. We only had the force of gravity acting upon the sphere, while in reality there's another force opposing motion. This is the drag force. It occurs when an object has velocity and is pushing molecules out of the way. The force of drag is dependent on the velocity of the object, represented by drag force is equal to a proportionality constant times the velocity squared, where k is a constant depending on the shape of the object. Including drag, our model becomes much more complicated because the drag changes with velocity, meaning that the force of drag is continually increasing. With non-constant force, the Fnet must constantly be re-evaluated using the new speed. In the next computational model, I used an iterative process to recalculate the Fnet, velocity, and position after each 0.3 second interval. To calculate k, the proportionality constant of drag force, I used trial and error, tuning k until the final position was the same as the final position in my Tracker mod. And you can see that the trend line for Tracker in green is significantly more similar to the gray model with drag than the yellow without. Comparing all three models, taking drag into account was closer but not perfect. We assumed that within 0.03 second intervals, the force was constant. However, this isn't really what happened. The force was really changing continuously, and we only estimated using these time intervals. If we'd been continuous, we would get a model that was much closer to our actual observations. If drag force is continually increasing with increasing speed, what happens when drag force is equal to the force of gravity? We know that Fnet would be equal to 0, and therefore there would be a constant velocity. This is also called the terminal velocity. When the force of drag equals the force of gravity, the velocity will be constant because Fnet is equal to 0, and therefore the change in momentum is equal to 0. So, can the terminal velocity ever change? For example, when we throw an object down, would it be different than when we drop an object? Because the terminal velocity is dependent on k, it will not change regardless of your initial velocity. We proved this using several models in Glowscript. 2, when the initial velocity was lower than the terminal velocity, as shown. starting at -4 and -2 in the y direction, both evened out around 10.1 meters per second. The initial velocity was greater than the terminal velocity. The force of drag slowed the object so that it leveled off around 10.1 meters per second. Unless this k constant changes, the terminal velocity will not change because mg is always constant. We can use the momentum principle to accurately predict motion when force is constant and when force is changing. Our model becomes more accurate as we take into account forces opposing gravity, such as drag, but we can't calculate changing force with as much accuracy due to the intervals in which we assume there is a constant force.